Nike Hercules, Stripey XM33, Thor, Johnston Island was the center of launch and experimental activity for the 1962 high-altitude weapon effects testing termed Operation Fishbowl. But Johnston Island was only the core of Fishbowl activity. Radiating out in all directions from this tiny island, 800 miles southwest of Hawaii, were instrumented stations, 266 of them, at sea, in the air, and on land, encompassing a major portion of the Pacific Ocean, all geared to collect effects data from nuclear bursts at high altitudes. Now to set this broad stage in greater detail. Within the limited confines of Johnston Island itself, the operations testing and support facilities were crowded into every spare niche, including space between the existing Air Force Station plant and buildings, with some apparatus and offices crammed into World War II bomb shelters, including the scientific readiness team, task force control personnel, and launch control units. At the northwestern end of the island was the Thor launch complex, joined later by Nike Hercules and Stripey units, plus a second Thor pad. Fishbowl's line of more than 30 instrument rocket launchers with attendant checkout facilities were sandwiched between the island's runway and the shore. This Pacific Missile range ship, berthed at the island's lone pier, kept an electronic eye on the missile for range safety purposes. A beacon tracking system followed the scientific pods and rocket instrumentation and backed up the Pacific Missile range tracking and impact prediction systems. Standing offshore were 9 instrumented test ships, vital links in the Fishbowl effort, including the DAMP ship, acronym for Downrange Anti-Missile Measurements Program Ship, American Mariner. Pod recovery and surveillance ships, and an evacuation aircraft carrier, which took aboard personnel non-essential to the island operation during each event, completed the ship array in the northern hemisphere. On islands south of the equator, in Johnston's southern magnetic conjugate area, a variety of instrumentation to collect effects data was set up for Fishbowl. Stations dotted the American Samoa island of Tutuila, as well as the main islands of the Fiji and Tonga groups, and to the east, Rarotonga. After preparations in Samoa's harbor, Pango Pango, the instrumented motor ship Acania moved out prior to shot day to be on the station designated for each event, concurrent with the departure of the balloon launch vessel Haifufu. Fiji's jet airport at Nandi was the operating base for 3 Fishbowl aircraft. On each event, a KC-135 and 2 RC-121s gathered southern conjugate effects data. Closer to the equator, the coral atolls of Canton, Kwajalein, and Palmyra also held many of the trailers, structures, and antenna towers representative of the Fishbowl test effort. North of Johnston, 4 main Hawaiian islands, as well as French frigate shoals, Midway, and Wake Island, mark the location for many instrumentation sites. For each event, approximately a dozen test aircraft, including optical and I-burn experiment planes, rose from Oahu's Hickam Air Force Base and headed south. Also to the west on Okinawa, in the far north at Adak and Fairbanks, as well as at Palo Alto, California, instrumentation was operated for Fishbowl's test events. During the latter part of the operation, other stations were added. All in all, Of the 266 Fishbowl instrument stations, 156 were on land, while 10 ships housed 80 separate project stations. 15 test aircraft carried the other 30 stations. The need for the test work carried on at Johnston and its far-flung array was compelling, for it stemmed from urgent Department of Defense operational needs requiring that high-altitude phenomena resulting from a nuclear burst be defined with simultaneous direct measurements on military operational equipment. For while America had been making rapid strides in other aspects of missile technology, its investigation of high-altitude nuclear detonation effects had lagged due to the 1958 test moratorium imposed shortly after the nation's first look at nuclear effects at high altitudes. This initial exploration in 1958 was limited to 6 shots, with attempts to collect data with untried experimental instrumentation in an environment alien to the nuclear testers. From a ship in the South Atlantic, 3 small detonations, known as the Argus series, were launched and triggered aloft for the purpose of examining the Christophilus theory that a long-lived belt of trapped electrons could be artificially created by a very high-altitude nuclear explosion. Other effects on Argus, although measured, were not thoroughly documented. In the Pacific, as part of the hardtack series, 3 effect shots, Yucca, Orange, and Teak, were detonated at respectively 26, 43, 77 kilometers, primarily to provide information on the change of blast, nuclear, and thermal effects with increasing altitude. From hardtack's limited test experimentation, one lesson learned was that widely diverse quantitative effects were produced at different altitudes, including major electromagnetic disturbances, causing communications and radar blackout problems. The nature of each effect could be learned only by actual testing. More than the information they furnished, these 1958 shots indicated how much more there was to learn about nuclear burst-created atmospheric ionization. Filling this information gap after the 3.5-year lull was Operation Fishbowl's mission, carefully patterned to the Department of Defense's needs. These operational requirements shaped up into objectives centering around 3 main lines of inquiry. One objective concerned ICBM acquisition, tracking, and intercept problems. It was essential for both defensive and offensive planning that experimental data be obtained on the effects of high-altitude nuclear bursts on radar performance. Another objective dealt with the evaluation of ICBM damage and kill mechanisms. DoD needed an evaluation of the effectiveness of nuclear detonations at high altitude for killing incoming ICBMs, vital to the nation's anti-ICBM effort. This knowledge, in turn, would indicate the relative vulnerability of U.S. ICBM reentry vehicles. A third objective concerned communications blackout, that is, the loss of signals due to disturbances in the ionosphere caused by high-altitude detonations. It was necessary to know the ensuing effects on military command and control systems which require long-range communications. These military objectives meshed into the overall Fishbowl objective of gaining a vertical scale of information for various altitudes and yields. Included in the wide assortment of Fishbowl projects were thermal studies on eye burn, investigation of debris distribution, and documentation of the nature and transport of the magnetic field disturbance generated by high-altitude detonations. On Operation Fishbowl, nuclear detonations rent the sky 5 times over the Johnston Island area, each time during the hours of darkness. Of the 5 Fishbowl shots, the highest burst was the 400-kilometer Starfish event, launched by a pod-carrying Thor missile. Its yield was 1.4 megatons. In addition to the local phenomena, the transport of bomb debris and other charged particles in the magnetic field produced colorful. colorful aurora arcing into the northern and southern conjugate regions. Checkmate, like Starfish, did not display a well-defined fireball. Checkmate exhibited a moderate aurora seen in both the northern and southern conjugate areas. Kingfish's fireball was well defined and its aurora moderate. From these 5 events, we will offer a selection of the test instrumentation associated with the DoD scientific objectives, along with some of the preliminary results obtained. Any conclusions which follow must be tempered by the understanding that the measurements made are valid only under the conditions of the experiments. For the first objective, the rockets fired from these launchers along the Johnston runway played a major role in probing the capability of detecting and tracking incoming ICBMs. Some rockets, launched in conjunction with the burst, were positioned in time and space to chart radar transmission paths through the burst environment. The aim was to help establish the space-time parameters of various blackout phenomena involving fireball, X-rays, beta, gamma, and neutrons, as well as directly measure radar capability to track and locate objects, such as reentry vehicles and decoys. Guidance of anti-ICBMs through the blackout was also studied. This radar dish on Johnston Island scanned the sky to gain information on intensity and extent of the clutter produced. It mapped 3 frequencies of operational importance: 400, 800, and 1200 megacycles. RC-121 aircraft also measured the amount of clutter in both the north and south conjugate regions. On Johnston Island, passive radio frequency receiving instrumentation sought data on the effect of noise from the burst region on radar performance. All this instrumentation took the measure of attenuation, refraction, clutter, and noise, the chief electromagnetic effects on radar performance. A serious electromagnetic effect was attenuation in the vicinity of the fireball, both its duration and its spatial extent, neither of which was measured sufficiently on Operation Hardtack. Rocket-borne beacons launched at H+5 and 15 minutes to seek late-time attenuation effects obtained no readily identifiable results. On Kingfish, the damp ship observed radar transmission paths through the fireball region from a C-band beacon from H+5 to 25 seconds, observing complete blackout and loss of track during this period. A Johnston Island receiver observed severe attenuation at 950 and 4750 megacycles through the beta patch for 60 seconds. On Tightrope, severe attenuations were measured up to 1 minute after burst. While the attenuating volume was greatly reduced in size, the amount and duration of attenuation was still significant. Refraction effects from a nuclear burst are of concern in the high-precision target tracking of ICBMs in the terminal phase. Although radar on the damp ship and Johnston Island showed no gross refractive effects from any of the bursts, preliminary results indicate a refractive jitter problem under certain conditions, involving a rapid fluctuation in the apparent angle of arrival of returning radar pulses. It was present on all events, but most pronounced on bluegill and kingfish. Another electromagnetic effect important to DoD's search capability is clutter, which could hamper radar performance for a period longer than other effects. Radar clutter is caused by ionized air, ionized bomb debris, and electrons trapped in the magnetic field. All these materials reflect radar energy, giving rise to false targets on the radar scope. Our first consideration is the reflection clutter from the fireball itself. Confined to the visible fireball, it is most pronounced when a well-formed fireball is generated. Another problem is presented by field-aligned clutter, observed in that region of the sky for which the observer is at right angles to the magnetic field lines at E-layer heights, and within an azimuth of about 15 degrees to either side of magnetic north. Field-aligned debris provides a host of fluctuating pseudo-targets over a large sky area. A radar system can evaluate them as false targets, but by sheer numbers, they may grossly overload the associated computer, which must check out each one of them. Of the serious electromagnetic effects from the burst, least bothersome to radar performance is noise. Highly sensitive advanced radar systems are adversely affected by the detonation's broadband radio frequency noise, since it reduces the signal-to-noise ratio. These instrumented pods, utilized during the starfish, bluegill, and kingfish events, played an important role in the DoD objective embracing the study of ICBM kill mechanisms, as well as determining the vulnerability of U.S. ICBM materials to these effects. The pods, 3 on each Thor, were engineered to be deployed to pre-calculated positions from the burst, so oriented as to expose the instrumentation to the burst. All the pods housed similar instrumentation to gain data close to the detonation on blast, neutron, and gamma radiation. However, the instrumentation that recorded X-ray and thermal effects was somewhat different. The 3 pods on bluegill housed instrumentation to gain data on the thermal output and its effects. The starfish and kingfish pods concentrated on X-ray radiation and its effect on re-entry vehicle materials. Some thermal measuring devices were also carried on kingfish. Post-shot recovery of the pods involved ship and helicopter convergence in the area, drawn by radio signals, flashing lights, and green dye. Fished out, the pods were taken to the Johnston Island recovery area, where removal of the scientific instrumentation for inspection and preliminary data readout was conducted. The pod program was relatively successful despite orientation problems and loss of some instrumentation due to hard landings. Preliminary results are limited mostly to the observable effects on the numerous re-entry vehicle materials exposed. One other observable effect was the shadow cast as the X-rays swept past the raised instrumentation on the pod backplate. Specific quantitative values are not available yet from either the X-ray or thermal studies. However, X-ray impulses measured were near those expected. Meanwhile, the interpretative work toward application to the kill mechanisms and kill distances for various types of RVs is underway. For the DoD communications blackout objective, this station in the Fiji Islands was one of the many links in the group of simulated high-frequency networks set up for Fishbowl. Their function was to investigate the effects of high-altitude nuclear detonation on military command and control systems utilizing long-range communications. One project utilized oblique incidence ionospheric sounders in a controlled network to obtain data over 28 propagation paths covering both the primary and conjugate areas. Information was obtained on 160 frequencies in the range between 4 and 64 megacycles. Also for each event, existing military operational communications links throughout the Pacific area were monitored to determine the disruptive effects caused by the fishbowl bursts. In the high-frequency experiments, burst-induced ionization altered propagation conditions, but caused no widespread outage. After the detonation, usable frequencies tended to be higher than pre-burst values. On some paths, propagation conditions were enhanced by the creation of new modes or paths. Almost all conditions had returned to normal by H+2 hours, except on starfish, where effects were detectable Pacific-wide for 2 days. Checkmate caused some adverse effects on transmission paths within 700 kilometers of Johnston Island for about 30 minutes. Kingfish altered propagation conditions on paths within 2,500 kilometers of the burst point, as well as throughout the southern conjugate area for several hours. Bluegill caused blackout for about 1 minute of certain high-frequency signals whose paths passed within 200 kilometers of the Johnston Island area, with lesser effects observed on these paths for 2 hours. Tightrope produced no observable propagation changes. VHF and UHF communication circuits were not degraded by the high-altitude events. Encouraging results were obtained from a strategic air command experiment, testing its airborne communication system during several high-altitude nuclear bursts. Signals from an UHF transmitter on Johnston Island were received by a KC-135 aircraft in the area and retransmitted to a relay B-47, which in turn retransmitted the signal to Hickam Air Force Base. Communications were not disrupted on this circuit by the high-altitude events. Also, the fishbowl tests were all conducted at night. Therefore, the effects are not necessarily indicative of those produced by a daytime shot. Of the many other projects of vital military interest on Fishbowl, we shall give the results only on the iBurn studies. Rabbits and monkeys on airborne platforms and ground stations were exposed to the thermal radiation from both high altitude and atmospheric detonations. Chorioretinal burn results from the atmospheric shots, all detonated below 15,000 feet, confirmed previous data on the distance parameters for known yields. For contrary to expectation, bluegill produced extensive eye burning, the most severe of the series. No other fishbowl event produced burns except tightrope, where the moderate burns received conformed to predictions. We will summarize the results of Operation Fishbowl in their relationship to the DoD objectives. For answers on the anti-ICBM radar performance of acquisition, tracking, and intercept after a nuclear burst, the salient electromagnetic effects of attenuation, refraction, clutter, and noise showed the following results. The optical measurements documented the spatial, temporal, and spectral characteristics of UV optical infrared effects associated with the detonations in the burst area, as well as the southern conjugate region. In the POD program, concerned with the evaluation of AICBM damage and kill mechanisms, the pertinent finding to date is that X-ray impulses measured tend to confirm predictions. From the extensive measurements on communications blackout, some tentative conclusions can be drawn. VLF is relatively unaffected. However, rapid and persistent phase changes can be detrimental to navigational systems. LF is generally degraded, especially phase-locked systems such as LORAN-C. HF is extensively degraded, but can be improved by the use of a system for rapid frequency shifting. VHF effects are similar to HF, except for less severe absorption. The UHF line of sight is relatively unaffected. Utilization of all these results must reflect the limitations of the fishbowl experiment. The fact that all were night bursts, and that the effects were only based on single detonations. The communications problem resulting from multiple nuclear bursts would be serious, but adequate planning and technical sophistication should make it possible to maintain limited communications at all times. Besides the results on main fishbowl objectives, a host of valuable contributions were made by the many other participating projects. Since the list of findings from the 5 fishbowl events is a long and continuing one, with miles of records still to be reduced and analyzed, this report marks only a beginning in the Fishbowl Chronicle. With America now of necessity peering skyward in its quest for security, the results gleaned from 1962's high-altitude operation contribute both to this safeguard role and to scientific enlightenment on the effects of the atom above the atmosphere.